subscribe.
Hey y'all, welcome back. So it looks like today for our homework we're looking at combinations and compositions of functions. This whole first section is just about combining functions using our normal addition, subtraction, multiplication, and division operations. This first one is just f plus g of x. So what we're going to do is we're going to take the function f of x and add it to the function g of x. So we get x squared plus 5x plus 6 plus 2x squared minus 3. And although they're not necessary, it's a good habit to get into putting parentheses around your functions, at least for the first step, to make sure you've sort of written them out completely. So now I'm going to combine my like terms. I'm going to get 3x squared plus 5x plus 3. For number 2, we're going to be doing pretty much the same thing, except instead of addition, we'll be using subtraction. So we'll have like basically this first same exact couple of statements. It's just that when we combine, we're going to be subtracting the second function rather than adding it. Here the parentheses are a little bit more important because you want to make sure that you actually subtract each term in the second function. So x squared minus 2x squared would be negative 1x squared. Then we have 5x minus no other terms to combine that with, so it's just plus 5x. And then 6 minus negative 3 would be plus 9. For g over f, we've got 2x squared minus 3. This is like equivalent to just doing g of x over f of x. So anyway, g of x is 2x squared minus 3. And f of x is x squared plus 5x plus 6. Let's fix this up a little bit here. So what was it? X squared plus 5x plus 6. There we go. So you might look to see if there's a common integer factor or not even an integer, but just any factor that you can divide out. Don't divide out, like if you see you've got like an x plus 1 over x plus 1, don't divide that out because then you're eliminating the whole that we talked about in our rational functions unit. Those would not be equivalent. So the only thing you could really divide out is if you had a common like numerical factor, like a 3 over 3 or something like that. But otherwise, you're just going to leave this as it is. For number 4, we're multiplying h times g. Okay, so just to clarify this notation here, and you don't have to write this first step once you kind of understand what the new notation means, but I think it's good at least in the beginning to kind of get a feel for it. So we got h times g, which is going to be 6 minus x. Oh, there we go. Not sure what happened there. 6 minus x times our g function, which is 2x squared minus 3. And so we are going to FOIL this out. I'm going to assume that you guys know how to multiply out two binomials. I'm not going to go into great detail here. We get negative 2x cubed plus 12x squared. Let's see, what else we got here? Plus 3x and then minus 18. And no like terms to speak of here, so we are done. For number 5, we are subtracting. So we've got h of x minus f of x. So again, just make sure you have parentheses around that f of x as a reminder that you want to subtract each and every term. Here, so h of x is 6 minus x, and then we're going to say minus f of x, which is x squared plus 5x plus 6. So now we want to combine on like terms. We'll have negative x squared. Here we have negative x minus 5x, so that'll be minus 6x. And then we've got 6 minus 6 is 0. Okay, so that works out kind of nicely. And so our h minus f function is negative x squared minus 6x. For number 6, we have h plus f of x. So let's see here. There we go. So h plus f, we've got 6 minus x plus f of x, which is x squared plus 5x plus 6. And we want to combine all our like terms here, so we get the x squared. Here the parentheses are not as necessary. In fact, they're not really necessary at all, but it can be helpful to just really see the two functions grouped up like that. 6 plus 6 is 12. So there's 1 through 6. It looks like starting with number 7, now we're going to be evaluating these functions. So what I think I'll do here, since I want to keep these functions on the page, is I'm going to do a little clip here. I guess you can't really see what I'm doing here, but that's all right. I'm going to copy and paste this into the document. I don't know if this is going to work like I want it to. It looks like it is not going to work like, oh, look at that. It did work. All right, so I'm just going to keep this out to the side so I can refer back to it for these next few problems. I'll put a little box around it. Okay, so number 7 is f plus g of 1. Okay, so we already found f of g, or f plus g, right? It's this one right here. So we could just plug in 1 here, but I want to show you how to evaluate this because I showed you on the notes how to do it that way. But I want to show you something a little different here, and that is to actually evaluate these separately and then add up their sum. So, add up their two values. So if I can do f of 1 plus g of 1 and plug those into f and g separately. So f is 1 squared plus 5 times 1 plus 6. And then g is plus 2 times 1 squared minus 3. Now, I guess it's really debatable, like which one's simpler since we already did find f plus g, but you know, you won't always have that ready to go, which is why I want to show you this way too. So we got, what do we have here? 1 squared is 1, 5 times 1 is 5, that's 6, 2 times 1 is 2, and then we got a minus 3 at the end. So we get 6 plus 6, let's see, 6 plus 6 would be 12, 12 plus 2 would be 14, and then minus 3 would be 11. So you could do it either way. It really doesn't matter whether or not you add up the individual values here, or if you find f plus g first and then plug in 1. Either way is fine, but I do want to show you both ways so that you can kind of pick and choose which one you like better. So for number 8, it's definitely going to be easier to evaluate these separately. So we can say h of negative 2 times g of negative 2. Did we find h of g, h times g earlier? Yeah, we did here. You can imagine plugging in negative 2 into this, you know, after finding what it is, will take a bit more work than just plugging in negative 2 to these functions individually. Okay. So in other words, I'm going to plug in negative 2 into this h function, and then negative 2 into the g function, and then evaluate these separately. So you can see this is probably going to be a little faster than having to multiply them together and then plugging negative 2 into each one of these. So 6 minus negative 2 would be equivalent to 6 plus 2, which is going to be 8. 2 squared is the same as negative 2 squared, which is 4. So 4 times 2 is 8, minus 3 is 5. So we get 8 times 5, which is 40. All right, so starting with number 9, we're actually getting into compositions here. I think this is the first composition problem. So let's find f of g of negative 1. Now, just like with the combinations, you can work these two different ways. You can either find the composition first, or you can plug negative 1 into g and then plug that into f. But just for the sake of practicing finding these composite functions, I'm going to find f of g of x first. So I'm going to input g of x into f. So I'm going to have, you know, f of x is just x squared plus 5x plus 6 And then for each one of these x's, I'm going to input 2x squared minus 3. Now that I'm looking at this, I'm kind of thinking, you know, maybe I'm mistaken. Maybe it will be easier to plug it into G and then plug that into F. I think with the one that's going to be this long, it's probably going to be the way to go. But I'll go ahead and plug in -1 at this point. So everywhere where I see an x, I'm going to plug in -1 and then evaluate. All right, so this is a pretty long expression here. So let's go ahead and start simplifying. So you got 1 squared is 1 times 2 is 2. 2 minus 3 is -1. -1 squared is 1 times 2 is 2. 2 minus 3 would be -1 again. So -1 is what g of -1 equals, which is why I'm kind of thinking it might have been easier just to calculate that first. And then -1 squared is 1. 5 times -1 is -5. So we got 1 plus 6 is 7, minus 5 is 2. And there's number 9. Let's clean this up a little bit. Make this a little easier to read. There we go. So for number 10, we have g of h of 3. That's the same thing as saying like g, try to write it out here, g composed with h of 3. Ugh, that looks terrible. Here, what I'll do here is write it like this. G-O-H, like this. So you can see it written either way, but the point is we're going to evaluate h of 3 and then plug that into g. So I'm going to work this out differently than how I did number 9 and 8, where I just plugged it into each function individually. Here, what I'll do is just plug in 3 into the h function and then plug that output into g. So first let's evaluate h of 3. So h of 3, let's go back to equation mode here. So h of 3 is going to be 6 minus 3. Okay. So h of 3 is 3. And then we're going to take that output and substitute it into the g function. So we'll have g of 3. It won't always be the same like this. This just kind of happens to be the way it worked out. But here we'll have g of h of 3, which is 3. So g of 3 will be what we get when we plug in 3 into the g function, which is 2 times 3 squared minus 3. So we can say that g of h of 3 is going to equal, let's see what this is actually going to come out to. 3 squared is 9, 2 times 9 is 18, and 18 minus 3 is 15. So g of h of 3 is 15. We'll work out number 7 the same way here. We'll first find h of 7. I forgot that I had it written over here actually. So h of 7 is going to be 6 minus 7, which is -1. So that's h of 7. So what we need now is g of -1. We're going to substitute this h of 7 into g. And g is 2 times x, which is -1 in this case, minus 3, squared minus 3. So we can say that g of h of 7 is equal to whatever this equals. So -1 squared is 1, and 1 times 2 is 2. 2 minus 3 is -1. Let's get this out of the way before we do number 12. bring it down here a little bit. Okay, so here we've got sort of some unnecessary parentheses out here. But we're doing h of f of x. So here we're not actually evaluating anything. We're just trying to figure out what this function is. So we're going to substitute f of x into h. So just as a reminder, the other way you could write this is h of f of x. Okay, these mean the same thing. Okay, this notation here. This one over here, on number 11, you could have written as g of h of 7. It means the same thing. So here, we got h of f of x. So what we're going to do is we're going to take this entire f of x function and plug it into h. So let's start by just writing out what h of x is. H of x is 6 minus x. So if I'm going to substitute in f of x into there, I need to have 6 minus f of x. Okay, so f of x in this case is the x squared plus 5x plus 6. So here we have x squared plus 5x plus 6. Okay, and then we can just go ahead and simplify this. So we get negative x squared minus 5x. And then we have 6 minus 6 is just 0. So this would be the end. That's it. For f of h of x, we're going to substitute h into f. So we're going to take this 6 minus x and plug it into the f function. Okay, and then we'll have to simplify that. Didn't we already do that? No, we didn't do that. I thought maybe we did, but I guess not. All right, so f of x, we'll start with that, is x squared plus 5x plus 6, but we are going to substitute in here h of x. Okay, so we're going to put h of x here and h of x here. And I'll just show this as two different steps just so you can really see how this is going to play out. So h of x here is defined as 6 minus x. Now because we're just dealing with the expression here, all we can do is simplify this. So we get f of h of x is equal to, see if we square this out, what we're going to get is negative x squared minus 12x plus 36. And then if we distribute the 5, we're going to get 30 minus 5x. And then we have this plus 6 hanging out to the end. So now I can go ahead and combine my like terms here. I've only got one squared term, so it's going to be negative x squared. Then I look at my linear terms. I've got negative 12x minus 5x. That's negative 17x. And then looking at our constants, we've got 36 plus 36 is 72. So all this is just 72. And there we go. So if we want to write it using this notation, we would say f, just use an O for now, but really it should just be like a circle, equals exactly this. Remember that these two notations essentially mean the same thing. Sometimes it's just easier to write it like this when you're trying to interpret what's going on. Now number 14 is a little weird because we're going to input h into itself. Okay, so let's start with h of x. What does that equal? Okay, that's the 6 minus x function that we got over here. So 6 minus x. Now what we're going to do is we're going to input h of x into that. So don't get thrown off that this is actually the same function, but we're going to say 6 minus h of x. H of x in this case is 6 minus x. So this right here should be 6 minus x. Now we can simplify it. We've got 6 minus 6 is 0, and minus negative x, so this is just going to be x. Yep, there you go. For number 15, we have f of g of x, so we're going to substitute g into f. So let's start with f. This is going to be kind of a long one. F of x equals x squared plus 5x plus 6, and we're going to substitute g of x into the equation. So everywhere where we see x, we're going to replace that with g of x. Okay. Now we're going to replace the g of x with what it equals. So that's the 2x squared minus 3. Did we find this before? I feel like maybe we did. 5 times 2x squared minus 3 plus 6. There we go. Okay, so now we just need to simplify it. So we're going to square that this first binomial. And so we give 4x to the 4th minus 6 and 6 would be 12x squared plus 9. We can also distribute the 5 here and get 10x squared minus 15. And I'm just going to leave it here for now. My next step is going to be to rewrite this, simplify, combine my like terms. Looks like I've got 2 quadratic terms. Negative 12 plus 10 is going to be negative 2. And then we've got 9 plus 6, which is 15. Minus 15 is 0. So we just get 4x to the 4th minus 2x squared. And there's number 15. All right, well, that finishes up the first page. Guess we don't really need this anymore. So let's take a look at the next page. All right, for numbers 16 and 17, we're using the tables to determine these. Both of these are basically asking for the same composite, f of g, just written in 2 different ways. And so what we're going to do is we're going to solve this out similarly to how we did with the equations, but instead of actually computing anything, we're just going to look at the table. So if we're doing f of g of 9, one way to think about that is we want to evaluate g of 9 and then substitute that into f. So you'll go to the table for g, find where x is 9, which is right here. Okay, so x is 9, so that means g of 9 is 12. Okay, so g of 9 is 12. So now we want to evaluate f of 12. So we look for where x is 12. And in the f table, so the table of values for f, when x is 12, f is 5. So this whole thing will equal 5. And that'll be our answer for 16. For 17, we'll do kind of the same thing here. We'll first evaluate g of 5. So g of 5 here is going to be 6. Okay, so we're going to have f of 6. So we're using the output of g as our input for f here. So we're going to input 6 into the f function, where x is. And then so f of 6 is 7. And so that'd be our answer for 17. So we're kind of doing the same thing, a little easier here where we have the table. Not too bad. For number 18, again, we're doing kind of the same thing again, except we're using the graphs. Are these the same graphs in the notes? They might be. But let's just go ahead and evaluate these anyway. F of g of negative 1. So here we're going to evaluate g of 1 first. Okay, so g of 1, we're going to look at the g table, go to where x is 1, and the y values, negative 1. I guess it turns out to be the same thing here. G of negative 1 is also 1. So this will equal f of 1. And then, so now we're jumping back to the f table. F of 1 is 3. For number 19, we've got g of f of 2. So we'll evaluate f of 2 first, which is going to be 0. So then we're going to take that output of 0 and input it into the g function, which will output 2. For number 20, we have f of g of negative 2. So we're going to start looking at the g graph, go over to where x is negative 2, and my output is, well, negative 2. So we've got f of negative 2, which is going to be negative 2. Oh, wait, is it? Actually, no, let's go back. F of negative 2 for the f function is, there's nothing there, so we're going to say that that's undefined. Yeah, no value here. For note 21, we're going to input f of 4 into f. So f of 4 is going to be 0, right? And then so if we input, if we do f of 4 as 0, then now we need to evaluate f of 0, which will be 8. We can find that right up here. So as you can see, we pretty much are doing the same thing whether we're given an equation or a table or a graph for these composite functions. We're just substituting one into the next. So in number 22, it's saying find the values of x that make f of g of x equal to -1. So we're saying f of something, f of that g of x is -1. Right? So what we need to do is figure out what is the something here first, and then we'll figure out what x is. So f of what is -1? So we look at our graph of f, and we say, okay, well, there's only one place where it equals -1, and that's right here at x equals 1, 2, and 3. So this number needs to be 3 to make it a true statement. F of 3 is -1, so that means that g of x is 3. And so now we're going to look at the g graph and figure out what x values have an output of 3. So let's go back up here, look at my g graph. It's 3 right here, and so this is going to be a case where we have to estimate this value right here. It looks like a little bit more than 3.5, so I'm going to call it like 3.7, roughly. And so I'll just say that x is approximately 3.7. For number 23, we're trying to find where g of f of x is equal to 1. Okay, so g of something is equal to 1, right? So we're trying to figure out what that something is first, and then we can kind of set up another equation here. So we're trying to first figure out where is g equal to 1. So we're going to go back up here. Let me erase my little markings here so we don't get confused. So we want to know where is g equal to 1. So there's actually, it looks like 3 locations here. Okay, g is equal to 1 at -1, at 1, and at 3. So we're actually going to have 3 separate x values that give a g value of 1. So we can say that f of x can either be equal to -1, 1, or 3. Okay, so this is going to basically split up into 3 separate problems here. So in fact, I might write it like this just to make it real obvious that we're doing 3 separate problems here. F of x could be any one of these 3 numbers. So we're going to go look at the f graph and see what x values make it -1, 1, or 3. So let's look back up here. So f of x is equal to -1 when x is 3. We already answered that over here for this one, right? And then f of x is equal to 1 at 2 locations, here and here, right? It was equal to -1 right here, so we've got like basically 3 values here. And then for the last one, where is f of x equal to 3? That's going to be right here, so that's going to give us even 2 more values. So we're actually going to have a total of 6 solutions here. These two are going to be estimates, but the other 3 should be exact. So let's go ahead and start listing them out. Just from left to right here, we say x equals, that's going to be 1, and we'll say about 1.5. And let's see, 3, so let's include 3. And then after 3, we've got this mark over here, which is about 4.5, maybe a little bit less, but I'm just going to call it 4.5. And then lastly, we've got 5. So this 1.5 and 4.5, these 2 are just estimates. So I'm just going to make a little note here that these are not exact. This one and this one. I'm just going to make a little note here. These are estimates. All right, but all in all, those are going to be your solutions that will make this statement true. So that wraps up the second page. Let's take a look at page 3. For these next 3 problems, we're going to be using these 2 functions defined above, f of x and g of x. And here, we're really doing the same thing that we did on the front page, where we're just either evaluating at a certain value or actually coming up with a composite function. So here we'll evaluate g of 1 first. So g of 1 here is going to be what we get when we plug in 1 into the g function. So that would be negative 3 times, was it 1 or negative 1? 1 plus 1. And so that would be negative 3 plus 1. So negative 3 plus 1 would be negative 2. So now we need to evaluate f of negative 2. So we're going to substitute negative 2 into the f function. So 2 times the square root. Let's see if we can get up. Square root always kind of messes with me here. 2 times the square root, there we go, of x plus 3, where x is negative 2. So negative 2 plus 3 is just going to be 1. The square root of 1 is just 1 times 2 is 2. So this is what we get. For 25 and 26, we're actually going to come up with an actual function instead of coming up with a value. So for number 25, we've got g of f of x. We're going to substitute f of x into g. So let's first write g of x. G of x is going to be, so g of f of x is going to be, first let's write g, which is negative 3x plus 1. And we're going to substitute f into that. So we're going to plug in this 2, so we'll say times 2 times the square root of x plus 3. And then to simplify this, there's not a whole lot we can do. We're just going to do the negative 3 times 2, which is negative 6. So there we go. There's g of f of x. Now let's find f of g of x, and I think we'll see that we don't get the same thing, and really the point here is that the order makes a big difference here. So if we have f of g of x, we're going to be substituting g into f rather than the other way around. So we're going to take the f of x function to, well here, I've got it written over here, and we're going to substitute g of x in right here, so negative 3x plus 1. And then from there we just need to simplify. So we've got 2 times, let's see, the negative 3x stays the way it is, then we've got plus 4. All right, so there's number 26. Now let's take a look at 27. This says that f of g of x is 3x plus 4 squared. Which of the following could be true? Well, if f of x is 3x plus 4 and g of x is x squared, f of g of x, if we substitute x squared into this, what we're going to get is, so this is kind of going the wrong way, it's 3x squared plus 4, so yeah, it definitely cannot be A. If it were B, and we substitute this in there, we're going to get 3x plus 4 squared, so I'm pretty sure that's going to be our answer here, but it might be worth checking out some of the other answer choices. Okay, C, if we substitute g into x here, or g into f rather, just the 4 squared, we get 3 times 4 squared squared. There's not even an x in this whole expression. I mean, we can actually just simplify this. It's definitely not 3x plus 4 squared. And finally, if we do the last one and substitute the square root of x into 3x plus 4, we're going to have 3 times the square root of x plus 4, and that is not the same either, so it's definitely B. For number 28, same kind of question here. It's saying if f of x and g of x, which is f of g of x? We're going to substitute g into f. So if f is 4 minus x squared, and we substitute g into that, let's put that in parentheses here, 1/2 x minus 2, looks like we're going to need to simplify that to really get our full answer here. So the 4 I'm just going to leave alone for now, the 4 minus. And then if I square this, that'd be 1/4 x squared. And then minus, we have, well, we'd have minus x would be minus 2x. And then plus 4. So if I do the 4 minus, I'm going to end up with negative 1/4 x squared plus 2x, and then 4 minus 4 is 0. So that's just this. Looks like our answer is going to be B. With number 29, we are both adding and multiplying the graphs of these two functions here. So what we'll do first is just kind of go point by point, and then we'll talk about exactly how to connect the dots. So when x is -2, we can see that if we're trying to do f plus g here, we're going to add the two y values. So we're going to add 1 plus -2 is -1. So when x is -2, y should be -1 if we're adding the two y values. Oh, that is not a circle. Let's try to make that a little better here. Okay. Then we'll go to x equals -1, where we're going to add 0 plus 1, which is 1. So I'll have a point right here. Then we'll have a, let's see, 0 plus -1 is -1, so we'll be back down here when x is 0. When x is +1, we have -1 plus 2 is 1. And then when x is 2, we've got 1 plus 2 is 3. So we've got these points, although I would suggest maybe not connecting them right up front. I want you to understand what is really going on here. It might be nice to have an idea of what kind of segments we're actually adding together here so we can know what to expect the graph to look like. So for example, if we look at the x values between -1 and, I'm sorry, -2 and -1, so in other words, I'm looking at this segment plus this segment, and think about what are the actual functions that would create a graph like this. And so I'm going to ignore everything else, but just look at this one segment. This segment is going to be constant, right? It would be like if we had y equals 1, right? It's a horizontal line. And so we could say, at least for this segment, y is 1. But for this segment down here, it is not a constant. We can see that it's we would have to write like a linear function, one that has a slope that goes up to over 1, so a slope of 2. And then if we continued that on, we would see that the y-intercept would be 2. So this one would be like y equals 2x plus 2. So if we were to add these two together, what we would get is 2x plus 3, right? If we combined 2x plus 2 plus 1, we would get 2x plus 3. Now, I'm not going to go through every single one like this, but what I'm trying to illustrate here is that our combination here, when we add these two functions, we end up with just another linear function, right? This is not quadratic, it's not cubic or anything like that. So we can expect that the sum of these two functions should be linear, meaning like it should be a straight line. If we were to continue this on, we can see we've got the slope of 2, and we could see that if we were to continue that line on, we would intersect 3, which matches up with the y-intercept that we calculated down here. Now, we don't have to go through each one of these. We might want to think about it a little more carefully once we get to the multiplication. But instead of like having to figure out each individual equation here for each individual section, we can think more about what kind of function it is. So like this next section, we have a linear plus a linear. Okay, they're both lines, right? So when we add two linear functions and combine our like terms, we're going to end up with another linear function, right? Like if this is negative x and this is negative x plus minus 1, if I add those together, all I'm going to get is negative 2x minus 1. which is going to be a linear function. So I can expect kind of a straight line here. Now, all the segments here are linear. You do have these two constants on the g function, right? This one that we talked about here and then this one over here. But adding a constant to a linear is still going to end up being linear. So that means for each one of these segments, they're all going to be just kind of a straight line here. Okay, so we can connect the dots with straight lines. And that's what f plus g would be. Now, f times g is a little trickier. We're still going to get the endpoints kind of the same way here, where we're going to multiply the y values of each individual endpoint. So, like for the first one, when x is -2, we can multiply -2 times 1 and get -2. If we multiply 0 times 1, we get 0. 0 times -1 is 0 again. Whoa, doesn't need to be that big. Then when x is 1, we have 2 times -1 is -2. And then finally, we've got, what was the last one over here? 1 times 2 is 2. So before we start just, willy-nilly connecting these dots, we want to think about like what exactly we're going to get when we multiply the functions together. So going back to like these first two segments, this is what we would get if we added them together, right? Maybe I'll say, instead of calling this y, I'll call this g of x, just to make this a little clearer. And it's just this one little segment. G of x doesn't always equal 1. It's just for this, what we have between these two dots. So this like little blue section. And here's f of x, right? So when we added these two functions together, we got, so this is like the f plus g of x. We got 2x plus 3, right? Just want to clean this up just a tad. Now, what I want to do is compare this to what we would get if we multiplied them. So if we multiplied these two, f times g, we would have 2x plus 2 times 1. Okay, so 2x plus 2, that whole thing, times 1. Now, if we multiply anything by 1, we're just going to be left with what we have. Now, I don't need to necessarily worry too much about exactly what the function is. I'm more thinking about what kind of shape does it have. So since this is a linear function, like a y equals mx plus b function, I can be pretty certain that the segment that will connect these 2 points on the product graph is going to be linear. Now, if I multiply a constant number by a linear, I will always get a linear, right? Like no matter what the constant is, whether it's 2, 4, 6, 8, whatever, even the negatives, fractions, anything, it's just going to end up like distributing into whatever the linear is, and you'll just end up with a linear. So for most of these other pieces, my product is going to be a line. So there's one that doesn't happen, but like if I look at like this segment and this segment, for instance, so if I'm multiplying these together, I'm multiplying a constant where the y value is just 2, so like 2 times, and then whatever the linear function here is. Looks like it might be like 2x minus 3 if I had to guess. So if we had 2 times 2x minus 3, we would just have 4x minus 6, and that's a linear function. So that means that these two dots are going to be connected. This is going to be the same for these two segments right here. I've got a linear, this 2x, and then a -1. So if I multiply -1 times 2x, I'm just going to get -2x. So that segment should be linear also. Basically what I'm trying to get across here is that a constant times a linear is always a linear. The one where it kind of gets a little funky is when we multiply a linear times another linear. Okay, so like this segment times this segment. Okay, so this one I want to break down a little bit further so you can see exactly what it's going to be. So this segment up here is going to be, like if we were to write it as a function, It's got a negative slope, -1, and then it's y-intercept 0, so it's just negative x. This yellow's not really turned out very good. Maybe I'll change it to like, yeah, we're gonna have to change the color here. What have we not used yet? Just make it black. All right, so that would be negative x. So here, I'll just maybe put it down over here. So this would be negative x right here, and then this segment down here would be negative x minus 1. So we're going to multiply this times negative x minus 1. When I multiply those together and I distribute that negative x, what I get is x squared plus 1. Plus x. Now, what does this mean? What am I really trying to get at here? What I'm really trying to show is that, I don't really need you to figure out, exactly what this function is, but what I do want you to know is that when you multiply a linear function by another linear function, what you end up with is a quadratic. And so between these 2 points, they shouldn't be connected by just a straight line, right? Because like if I multiply any of these other 2 y values, it's not just going to be 0. Instead, you'll have like a little tiny quadratic, a little parabola, or at least a piece of a parabola. Now, the only sort of outstanding question here is, is it going to do something like this, or is it going to do something like this? And our clue is going to be in the fact that we have a positive leading coefficient, so we know it's going to open up. So the last piece should be sort of like the bottom portion of a parabola that does something like this. And again, you don't need to know exactly what it's going to look like, but just know that it is going to be a little curved here because we're multiplying a linear by a linear. So kind of a weird problem here. If this is kind of confusing, maybe go back and try to work it out piece by piece. I didn't show every single multiplication, but yeah, so there you go. That's what your graph should look like. For number 30, just really more the same as what we did earlier. So we're using, instead of just like 2 tables and 2 graphs, we've got a combination of a graph and a table. So we'll just evaluate the inside function first and then plug that into the outside function. So for 30a, we've got f of g of 4. So first we'll evaluate g of 4, and we can see on the graph that g of 4 is 2. Right? Like if I go over to 4 in my x, my output is 2. So we're going to have f of 2. So make this a different color, make it a little easier to see here. And then we're going to evaluate f of 2. So this is where we'll use the table. We'll find 2 on our x's, and we can see that our value of the function should be 3. So 30a should be 3. 30b, we're going to evaluate f of 1 first. So f of 1 is going to be 5. So then we're going to evaluate g of 5, which from the graph, we can see g of 5 is 0. When you have this composite function notation, I do think it's easier if you rewrite it kind of like how a and b are. So I guess what I'm saying is instead of writing it as like f o f 0, if you think about it like using the other function notation like f of 0, sometimes it's just easier to figure out what the answer is going to be when you write it like this. So first we'll evaluate f of 0, and according to our table, f of 0 is 2. So since f of 0 is 2, we can now evaluate f of 2. So we're kind of staying with f here. F of 2 is 3. For g, we're going to first evaluate g of 0, right? Because this is really g of 0. And g of 0 is 1. So then we evaluate g of 1, and we get 4. F of g of 1.5, so g of 1.5, looks like it's going to be right here, that's going to be 3, right? Yep. So f of 3 And then so we'll use the table to evaluate f of 3. You can see f of 3 is 4. All right, our last problem here says use the figure to find all solutions to the equations, f of g of x equals 0 and g of f of x equals 0. So first we want to know f of what is 0, right? So then we'll be able to set an equation g of x equals something. So f of what equals 0? So if we look at the f function, we see that f equals 0 in 2 locations. Okay, so here's where f is 0, right? Here and here. So that's going to be at 0 and 4. So there's going to be 2 separate places for 2 separate x values where f is equal to 0. So we can say that either g of x has to be 0 or g of x can be 4, right? Because those are the 2 x values that make f 0. All right, so now we're going to look at the g function and figure out what x values make g 0 and what x values make g 4. Well, the x value that makes g 0 is 4, and the x value that makes g 0, 4 is 0. So the x value that makes g 0 is 4. And the x value that makes g4 is 0. So these would be the 2 x values that would make f of g of x 0. For b, we're going to kind of think about it the same way. All right, so first, we want to know g of what is 0. And so we're going to look at that g function. And there's only one location here where g is 0. Okay, g is going to be 0 right here when x is 4. So when this input is 4, in other words, when f of x is 4, then g is 0. So now we need to say, okay, well, when is f of x 4? Well, f of x is going to be 4 when x is 2. And that's it. So that's it for tonight's homework. Let me know if you guys have any questions or need any clarification. But other than that, I'll see you all next time, and have a great day.